Okay, so remember our objective is to show whether the current and voltage are really out of phase, no? Using the differential equation. So in this case, first order differential equation. And most of the time, in this case, we have, if you notice, we have here. Okay. Um, now for the capacitor, our our idea here is the current. Okay. So actually, the current is the one, the given, no? Supposed to be the given, the current. So let's see. Okay, so here we can use the PC of T, no? That's the voltage across the capacitor. Okay, so still they are the same. Okay, VC of T and Vs. But in this case, we cannot use VC of T because VC of T is now a variable. No? I mean, it's the concern. Actually, we need to use the KCL, no, in this case, because the capacitor is dependent on the current of the capacitor depends on the changing voltage. So we can think of voltage as the variable. In the previous one, we treat uh, we treat we treat the current as the variable. So that's why our solution here is current. So in this case, we try to use the current. Okay, and in a way, our goal is to show that the current and voltage is out of phase by 90 degrees. Okay, so can assume that current is Im sine, okay, sorry, sine W plus theta. So theta is whatever value. Okay, so anyway, using KCL, you know that Is, okay, so this is Is of t is equal to the I of t. Okay, I hope it's Is of t is equal to I of t or Ic of t. We can set this one as Ic, the current flowing to the capacitor, from the source to the capacitor. So, okay, so Is t C D. Actually, sorry, I think we don't need to do this pala. We don't need to do this. So we just stick to the voltage, no, because we can get the Is of t. And we know that Ic of t, sorry, Is of t is equal to C dV C over dt. Now we know that the voltage across the capacitor here is equal to the voltage across the source. Vc of t is equal to Vs of t. It's obvious, okay? So the polarity are the same. Okay, so and then the current is the same. So okay, so we have here Is of t plus C d Vs of t divided by dt. Then changing the values there. Okay, we can cross multiply, and yeah, you have Vs. So you don't need to, should be capacitor anyway. So that's it. Vs of t and then Is of t dt. Okay, so our goal pala is to get the current. Sorry, the voltage. So we swap the two. So we have the Vs of t is equal to 1 over C Is of t dt. Okay, so just go back to the original plan. So we're given with the current source, which is Im sine Wt. So our voltage is unknown in this case. Okay, so to make it simple, actually we can We can do the same with the inductor, but I'd like you to follow the same pattern. Okay, so then taking the integral, okay, you can replace is of t and sorry, 1 or c, then is of t is im sine wt plus theta dt. Then we can take the integral from 0 to t. Then here dvs of t 0 to t. So we have here vs of t minus vs of 0 equal to 1 over c. Now actually, by letting again, just the same with the inductor, so you have uh, let u is equal to wt plus theta. Now du is equal to wdt. So therefore dt is equal to du over w. So here you can still have negative one, now negative 1 over wc, and then integral from 0 to t. So we just ignore that one, sine u t. So in a way, here is a new term. Okay, new values. Then so by looking at the circuit and assuming that initially there's no charge, t is equal to 0, it is off, or before 2 t equals 0 is off. So this one we can treat this one as 0. Okay. Then vs of t is equal to negative 1 over wc. Then cos, sorry, why is it negative? Not yet. Here, negative cosine. So negative cosine, okay? Cosine u, then u is wt plus theta, and then from 0 to t, okay? And then can arrange this one. So it's similar to the previous cosine wt over wc. Sorry, I think I have a problem. I'll turn off my cam just for you to, okay, to make my computer faster. So this is C, then cosine wt. So that, sorry, I think t plus c. Okay, and yeah, if, sorry, I forgot the theta here. Okay, so sorry, what I'm doing, I think I mistake here. Plus theta, and then the other one based on 0, so we treat that one as c. Okay, the same as the previous example. So we make this cosine positive, so this is cosine wt plus theta plus 180. So now it's positive, and then converting this one to sine because our current is sine. So we just simply add by 90 degrees. And so it becomes 270 or negative negative 90. So this is Vs of t is equal to, sorry, I forgot the magnitude of your current Im. So Im, I forgot the Im. That should be Im over Wc. then sine Wt plus theta minus 90 degrees. Okay. Now, if you look at this is voltage and then this is current. And the inductor, you have the current. The current is lagging by negative 90. Okay. So if you draw this one, so if you draw this example, so we have your I. This is your IS, and then your VS is here. Okay. In our video, we have the voltage here, and then your current is here, which is the same. Okay, because they are 90 degrees out of phase, positive. Okay, so therefore, if you want to construct this one, so this is V Vs is equal to I, sorry, Im, just amplitude first divided by Wc. I think I made a mistake somewhere. Yeah, that's right. It's okay. And then angle negative 90 degrees. And you can see that to make them similar, angle 0, sorry, that's magnitude first. Im angle 0, then Wc angle 90 degrees. Then this one becomes Is divided by JWc. Now, from the formula V is equal to Gi, therefore, our Z here is equal to 1 over JWc. Okay? So this is these are the important thing you need to. So because of this, actually, if you think the voltage and current are actually in phase, the source are in phase, but because of this reactance or impedance, because of this one, um, the voltage and the current are now out of phase by 90 degrees. Okay, the same is true for the inductor. For the inductor, they are out of phase by 90 degrees because of the presence of an inductor. So inductor is simply to delay, to delay the current. So you can imagine a current flowing here, and then because if it is coil of wire, so therefore the current is delayed, by 90 degrees. If it is pure inductor, but in reality, actually, in reality, there's always a resistor present or resistance present in the circuit. Okay, so unless it is superconductor, okay, but so this thing is only in theory. Okay, but I'd like you to appreciate the importance of the idea of the electrodynamics and electrostatics. Okay, so that you will appreciate also differential equation in your other subjects. Okay, so now if you want to use cosine instead of sine in your initial values here, for example here you want to solve for cosine, you will still end up with the same process and then the same thought. Okay, that maybe if you're using cosine, this will be but the same idea here, that the phase difference is 90 degrees. Okay, so you might wonder, why is it sine? Are there any standards? So as I said, there's no standard. No, mathematics is an expression, of the system. So you can express in many ways. Actually, we can solve this one using Laplace transform, and you can also solve this one using the phase source. Okay, so that the one we were talking about in the complex numbers. Okay, so that's it for the capacitor. And if you have any question, I would like to entertain your question. So in reality, there's no perfect or pure inductor circuit or inductive circuit, and there's also no perfect capacitor circuit. There's always small resistance, and because of this small resistance, okay, so the because of the small resistance, so the difference or the angle difference is not totally, is always lower than 90 degrees. Okay, lower than 90 degrees. Sorry, lower than, lesser than 90 degrees. So the angle here, okay, there, because of the small resistance. Okay, so that's it. Now, what do you mean by the current or the voltage in without the phase angle theta? So this is, we know that this is the real, no? So meaning that the voltage or the current is operating in a real manner, okay, in a real value, okay. And then the current corresponds to the system, okay. So meaning it's like here it's like the voltage giving you the source, and then the system responds. No, okay, this is our demand. So this is our passive device, right? This is our active. So the active will give you real something, okay? And then the passive device will ask you, okay, I need this. I need a reactive value of current. So the current, okay, in this case for the inductor is totally 90 degrees out of phase, no? Okay, but your voltage you're giving in real, so something like that. Okay, so I hope you appreciate the. So later on we will also discuss the similar things for a more complicated RLC, okay, RLC circuit, and we will use some of the differential equation later on. Okay, you have any other concern? Now next week we will have a quiz up to this point, no? Up to this point. So during the midterm exam, we will have our quiz number 3 and 4 together. So yeah, you 1.5 hours. So I will try my best to make it short, like maybe 1 hour lang. Tapos the rest will be some time for you to check your answers. Okay. And okay, so kanusta atong schedule gani next week? Tuesday or Thursday? I think Tuesday, no?